I can see that some of you are in vacation mode, and I think somebody also going to join us in short time. But let's go with Bindu's lecture. And I think she's going to talk about confidence interval and things like that. So, Bindi, it's over to you.
Yeah. So I'm just interested to know, I mean, what about Queen's College? I mean, how much did they cover anything in terms of research methodology?
Indeed, I think they have shared some videos and also two classes. One is on reflector search and the other one on critical appraisal.
Okay.
That's all what they have done.
Okay. Okay. And has everybody gone through the videos and stuff?
Yes, yes.
Okay. Okay. So today we'll just, we'll start with confidence intervals and then, okay, can you hear me? So let me see.
I don't know.
Can you hear me?
Yeah, I can hear you.
Okay. So we'll start with confidence intervals. Okay, just to, last time when I was taking the class, and as we said, we can't observe the population. Okay, we don't know what the population is. Okay, so what we do typically is we sample and then we want to really find whether we can say with confidence that this this sample belongs to the population. Okay, now it is very difficult to get a point estimate. um, are you feeling a background noise? Are you hearing some background noise? Okay,
No, no.
let me just switch on the AC and switch on the fan off the fan. Maybe that will be better. Just one second. Give me a minute. So the idea is that I mean we can't we don't know the population estimates. Okay, so we are sampling. Whole purpose of doing this is that when I take a sample, I want to know with what degree of confidence I can say that this sample belongs to the population. Okay, now I don't, it's very difficult to say that if I get an average of X, okay, I can't possibly say that the population is also X, right? So let's say my average of something is like 50. Okay, now can I say that in the population also it is 50, right? The population figure is also 50. Now that becomes very difficult to say. So what we do is that we compute a range and we say that we are Biju sir is not able to hear.
Sir, maybe you can try logging out and then rejoining. At times it happens when the connection is so. You can just log out and then rejoin. I hope that is.
Do you want me to wait for a second? I'll wait while you join in again. Would you like to log off and then you would like to log in? What we say is that I am 95% confident that this sample will lie between this estimate and this estimate. Okay, that the population figures will lie between this, and because I'm basically using a sample to construct my population estimate. I don't know the population. I'm just using a sample. So what I am essentially doing is that when I am computing all these statistics, I am trying to get at the true measure of a population estimate. Okay. So for example, whatever studies that you may be doing, you may be writing, a lot of research papers, and something, some particular aspect about a patient really, interests you. You want to study about the phenomenon, and you want to, maybe start a new course of treatment or something. So you take a sample, okay, and you say that, okay, fine, this requires some funding, and you want to really say that, this is important enough, and the incidence of this disease is fairly large in this population, and I therefore want funding. So you construct a sample. Now obviously I don't know the population, but by basis of that sample, and I find that the incidence of that population, and I can say that based on this figure, I am 95% confident that within the population, the incidence of this is going to lie between X and Y range, and I can say that with 95 or 90% confidence or 99% confidence. These are normally, three confidence intervals that we say, which is either 90%, 95% or 99% confidence intervals. So that is the purpose of using confidence intervals. Anybody has any questions before I actually share my screen? Right, the calculation and all is, it comes later, but first let's understand why we are doing this, right? And then once we do the confidence interval, then we go on to hypothesis testing. Anybody has any questions? Anybody would like to tell me something today that you feel that you want to take a, you want to do a research, okay, and what is it that sort of is going to interest you? What is it that you are interested to know about the population? Anybody would like to give me an example?
Prevalence of depression in the general population.
Excellent, very good example. Okay, so the other day I found somebody on LinkedIn asking me, whether somebody had done any research on depression, or some agency is working on depression in the young age population, that is like 17 to let's say 25. Okay, so we normally associate depression with senior citizens, but we are finding increasingly that even the younger generation is facing depression, and there are there is a high incidence, and which makes it a kind of a public health emergency. Okay, so let me just share my screen. Okay, yeah. Everybody can see my screen?
Yes, yes.
Okay. Let me just see. Okay. So I have just, focused on, the basics, okay? Which means you understand the concept and then you kind of, do this, okay? So here what we are assuming is that whenever we do these confidence intervals, okay, the sampling can be either from a normally distributed population with a known population variance, or it can be a non-normally distributed population with a known population variance. So, right, we'll come to t-testing little later, okay, because there, when you don't know the population variance and sample sizes are small, then that's a different thing. But right now, let us for the timing assume that the sampling is from a normally distributed population with a known population variance, which means I know that there is that standard deviation is likely to be this much. Okay, so in this case, right, the average of whatever it is we are assuming as mu, okay, and the the standard deviation is the population standard deviation divided by the under root of n. Okay, now if you have a sampling from a non-normally distributed population, okay, same thing, okay, but in this case you might have a finite population correction factor. Okay, so this n minus n and n minus 1 is okay is when you have a, your population size is not too large. You can disregard it when n is quite large, comparative to, so when you say n upon n is less than equal to 0.05, okay, when your sample size as compared to your population is less than equal to 5, but otherwise, okay, then you need to have this, you do this population correction factor. But in most cases we normally don't do it. We normally stick to the B part of it. Okay, the rest we don't do that. Okay, the finite population correction factor is not normally done. Okay, now just let's look at what we are trying to do. Okay, now if the mean and standard deviation of serum iron values for healthy men are 120 and 15 kilograms for per 100 ml. So 120 is the mean, okay, and 15 milligrams per. What is the probability that the random sample of 50 normal men will yield a mean between 115 and 120 milligrams per 100 ml? Okay, so we know the standard deviation. Okay, right? So this is 15 divided by under root of 50. So we have got the we've got the standard error in this case, which is 2.1213. Okay, now what we have done is we have computed something which is called the Z value. Okay, which is called the Z value, which is basically nothing but x minus mu divided by the standard error. Okay, so in this case I have found that, okay, my range is between minus 2.36 and plus 2.36. Okay, that means, right, it is in terms of, if I look at that population figure, okay, if I look at the probability, it will be something like 0.9818. okay, because I am computing two extremes. Okay, between two extremes I am looking at. So you have a plus 2.36 figure and you have a minus 2.36 figure. So based on that probability, right, the probability that it is going to be around 0.9818. Okay, so this is what I am saying is that, okay, if I do this sample, okay, what is the probability, okay, is that I am now 98.18% sure that if I do a random sample of 50 normal men, that will yield a mean between 115 and 125 milligrams per 100 ml. So this is one example of doing a confidence interval. Now if you see that this is the range that I am doing, is that my confidence interval that I am 98% sure it is between 115 and 125. Okay, now these are basically this is just computation. Okay, in this case you are looking at means of two populations. Basically you are trying to find out what is the difference between two populations. The way you do it is still very much the same, except there is a slight difference in the formula. Okay, so here in this case you are doing x bar minus x, x2, right, because it is two different, minus mu1 and mu2. Okay, and here in this case your standard error is the under root of, because you have two populations. Okay, therefore you are doing this kind of you are just adjusting the standard error because you are doing two populations. Okay, so for example, now if I look at this particular question, okay, it says for a certain type of a client, the average length of a home visit by a public is 45 minutes with a standard deviation of 15 minutes. And for a second type of client, the average home visit is 30 minutes long with a standard deviation of 20 minutes. Okay, now if a nurse randomly visits 35 clients from the first and 40 from the first, okay, what is the probability that the average length of home visit will differ between two groups by 20 or more minutes? Okay, so depending on the client, okay, one type of client, she says 45 minutes, okay, with a standard deviation of 15 minutes, and the second type of client, it's like 30 minutes with a standard deviation, right? And she visits 35 from the first and 40 from the second. Okay, Now basically trying to say that, okay, if I do this, okay, what is the probability that this difference is going to be by more than 20 minutes or so. Okay, so we are looking at this, right? So we have just basically compared. Okay, so in this case mu1 and mu2 is 45 minus 30. Okay, and the difference is 20, so you are looking at the difference between x1 and x2, which is 20 minutes, and the difference between the population was 15 minutes. And here you have computed an average of the standard error by looking at the respective standard deviations of the two. Okay, and when you are looking at this, your z score is 1.23. Okay, now if you look at the z score of 0.123, okay, right, somebody can use the calculator. That I have not put the calculator, but if you use the calculator, you will find that the value is 0.8907. okay, when you say 0.8907, so to the right of the is 1 minus 0.80 is 0.1093. So if you want to say that if the difference is more than 20 minutes, then the probability is 0.1093. Okay, so between 20 minutes, okay, but if you are saying greater than 20 minutes, okay, greater than, it is 10.93%. okay, everybody has got this, or do you have a question? Let me just stop share. Okay, let me just ask you guys. Okay, I know it's a little technical. Okay, let's discuss this before we go further. Anybody has questions? Why are we doing this? Forget about the calculations. I said, why are we doing this? Why do we need to know this?
To know with how much confidence or how sure we are that our statistic lies between so and so value.
Because I want to be sure exactly what is the probability of something happening. Okay, as I said, I mean, in this case, I have only got a population variance. Okay, and I have some estimate of the population, but I really want and in the future questions, I will not even have the population. Right, I will just basically, when I do the confidence interval, I will just look at consumer demand. But right now I have in this case, right now I do have a population figure. Looking at that population figure, I am right now saying that, okay, if I do this sample, okay, and if I do this, what is the range that I am going to get? Okay, right now it is this. Okay, as we go on further, let us do the confidence interval. So this is just a beginning to getting there. Let me just let me just get to this one. Okay, this is proportions, which is pretty much the same. Okay, I'll come to this later. Okay, now let's just first understand these terms. Population is all possible values. Sample is a proportion of the population. Okay, now statistical inference basically means that I have to generalize from a sample to a population with a calculated degree of certainty. Okay, now what I do is I either do a hypothesis testing, okay, or I estimate. Okay, now a parameter is a characteristic of a population. So when I am looking at a population mean, which is called mu, okay, and statistics is calculated from data in the sample. Okay, this x bar needs to be in that brackets. Okay, so that statistics, when I look at parameter, I am talking about population, and when I am talking about statistics, okay, then I will have something like an x bar, and which I am looking in terms of a sample. So parameter is from the population, statistic is from the sample. So that is one thing that you have to understand, is that statistic invariably means it is from a sample. Okay, now when I say statistical inference, it is I am making a conclusion about a population on the basis of whatever sample that I am drawing from the population. Okay? If I draw a single estimate, then it is a point estimate. But most likely we do not do a point estimate. What we do is an interval estimate, okay, which consists of two numerical values, which means a lower value and an upper value, which we say that between the two values, the population figure or the estimated population figure is going to lie. Okay, so we say an interval estimate consists of two numerical values defining a range of values that with a specified degree of confidence, right? And as I said, that degree of confidence can be either 95% or 90% or 99%, most likely includes the parameter being estimated. So we say that within this estimate, within this range of values, I am 95% confident that between this interval, my population parameter is going to lie. Okay. Sample population is the population from which one actually draws a sample, and target population is the population about which one wishes to make an inference. So my target population, I obviously, actually want to, it's my sampling frame, but based on whatever I have. Okay, so sometimes I may have a sampling frame, but what I actually sample may not be the entire sampling frame. I may use a subset of it, and that is called my sample population. Okay, these parameters, okay, when I say parameters, population, okay, when I say notation, mu stands for the population, and when I say statistics, it stands for X bar. Okay, the population parameter does not vary, but the statistic, so every time I sample, it can vary. Okay, it is not a calculated, but in statistics it does. It's actually calculated. Okay. Okay. Now, if you look at this normal distribution, I think we discussed it earlier. Okay. We talked about that 3 standard deviations to the right and 3 standard deviations to the left, okay, make up the entire normal distribution. Okay, so if you look at this is plus standard error of the mean. That when you say mu plus SEM, okay, it is 68%. 2 standard deviations is around 95% of the area, and 3 standard deviations has approximately 99%. Okay, that is why we normally say what we use is either 95% or 99%, which is either close to 2 standard deviations or more precisely 1.96, and 3 standard deviations is something like 2.58 or something. Okay, so this is this is the right. So there is this Chebyshev theorem which says 68% falls between one standard deviation of the mean and a normal. Okay, 27%, that is 68 plus 27 is 1 and 2 standard deviations of the mean, and within 3 standard deviations it is 99.7. Okay, so this is how the normal distribution range kind of looks. And when I say 68%, it means 68% of, you can also look at it at 68% probability. The area under the normal distribution is 0.68 in terms of probability. Then between 1 and 2 is 0.27, and the rest beyond that is, the entire 3 is 99.7 or 0.997 in terms of the entire area under the normal curve. Okay, so if you can just look at this, everybody can look at this. 0.3413 plus 3.3413 is 68%. Everybody can look at this. Okay, and if I calculate, this is 68.39%. Just 1 second, I'm just getting my calculator. So I have 0.3413 plus 0.3413. It gives me 68.26, 0.6826. And then I add 1359 plus 0.1359. It gives me 95.44 plus 0.0215 plus 0.0215. It's gives me 99.74 or 99.75. To be more precise, it's 9.9975. Okay. So this entire area is the rest, what is left in the tails is 0.0013. So if I'm looking at a 99% confidence interval, my tails will accordingly be calculated this way. Okay, I'm just going to stop here. Okay, let's just try and I know this is again technical. Okay, so what happens is when I draw a confidence interval, okay, so I say that I draw a sample and I get a mean, okay, and I say that my confidence interval is I draw a confidence interval and I say that it is between, let's say true population mean is between 55 and 60. Okay, now how does this 55 and 60 come? How does this 55 and 60 come? Before we go into formulas, I just want everybody to figure out why or how we are doing this. What is the logic behind it? What do you mean by expected mean or expected average? Okay, let's take an example of insurance, health insurance rates. Okay. Now, if I were to calculate health insurance premiums, okay, and I was to calculate health insurance or life, or let me take life insurance premiums. Okay, let me calculate life insurance premiums in a place like Mount Abu. Okay, where the violence is very low. Okay, and let me calculate life insurance premiums in a place like Bihar, where the violence is much higher. Okay, of course in this case the government of India doesn't allow variability, but let's say that the government of India allows the insurance to to price insurance on the basis of a city. Where do you think the premium is going to be higher? Where do you think? Is it going to be Mount Abu or is it going to be, let's say, Arya in Bihar? Where do you think the premium is likely to be higher?
Bihar.
Bihar. But why Bihar?
There is more chance of getting people injured and getting assisted with hospital.
So what is life insurance basically? What is, how do insurers make money? They don't want you to die, right? You keep paying premium, you live for a longer life. Great, they make their money. If your mortality rate is going to be higher, they tend to lose, right? Because they have to make payouts earlier. True? Right? So the variability in Bihar in terms of life because of whatever gun violence is likely to be higher. So where do you expect that the insurance premium range is going to be more? It is more likely to be in Bihar rather than in Mount Abu, which is, let's say, quite sleepy little town. Right? The variability is not likely to be higher. Because people will, good weather, less pollution, more sedate lifestyles. Okay. So essentially, what are we doing out here? We are looking at the variability component. The more the degree of the variability component, okay, the more the degree of the variability component, the greater is going to be the range. If I have a higher standard deviation, my confidence intervals are more likely to be higher. True? Everybody is confused. Very silent. Okay. Tell me which disease. Tell me if you have. Why are the premiums higher for those critical illnesses? If you take an insurance for critical illness, I'm assuming the premiums are going to be higher. Yes? They're likely to be higher, oh? Why are they likely to be higher? Because the risk is more. And how do we measure risk? It is standard deviation. Variability can either be, it can be, in the upward direction or in the lower direction.
Ma'am, if it was a critical illness, won't it be like all the patients will have higher cost, but it won't be?
Yeah, because there is higher probability of them dying, na? So there is, you don't know what is going to happen. The risk is going to be higher.
So there won't be more.
See, in a critical illness, a person can survive for 2 months, can survive for 6 months, and can survive for 3 years. And there'll be expensive medical treatments. Right? It can be, that variability can be very high. Right? Because you don't know what, you've taken a policy, okay, and that person contracts a critical illness, it can be years before somebody, it's not a quick death. So the variability, in terms of that, the risk factor is going to be obviously much higher. And you will end up spending more on medical treatment because somebody has been diagnosed. You'll be going for medical visits, and that, as I said, you don't know the number of years which you will be availing this kind of treatment. Okay, so the insurance policy is, the insurance company is exposed to far more greater risk. Okay, so the critical element is the risk factor. I'll give you another example which is from finance. Okay, which is so when you talk about a stock. Okay, so you normally assume that a stock can go up. Okay, but it can also go down. Okay, whether it goes up or it goes down, in both cases there is risk. Okay, somebody might have done a might have taken a position in a derivative which makes money, which he makes money if the if the stock market actually if the price goes down, he makes money then, and he doesn't make money if the stock market goes up, right? So it can be both ways. You can actually, if you are in a derivative position, if you have you have actually invested in derivatives, you can actually lose money if the stock market if the particular stock goes up. So the key out here is the standard deviation. What is the risk? What is the degree of variability? If the variability is higher, your confidence intervals are going to be much wider, which means that the difficulty of your lower range and your upper range of your population estimates is so much going to be larger. Okay, that is one factor. And the second thing is your reliability factor. Reliability, which means either you're doing it at 90% confidence interval, you want to be 90% sure. If you have 95%, then you are more sure. And if you are 99%, that means a higher degree of confidence. The greater confidence that you want, the estimates, the range of estimates will be far more. So there are two elements into this confidence interval. One is the standard deviation or the standard error, and the second is the reliability quotient, which can be either 95%, 90%, or 99%. The more confident that you want to be that, okay, my estimate will resemble will be between a population range, the greater will be the interval. How many of you have not understood? Please tell me. I'm happy to repeat.
So, ma'am, if the population has more of a like flattened or plateau-like, then the confidence interval will be much more wider. That's what you mean.
Can you repeat again? What did you say?
So, if the population is more wide, I mean the sample is wide, then the confidence
If this,
interval.
I would say population. I'm saying if the yeah, you can say wide, but if you are saying standard deviation, yes. Right? If there is more variability in something, okay, so it's like if you have, let's say, if you look at the number of patients coming into a hospital, okay, and you say that, okay, you want to compute the average, you want to say that in a particular day, what is the range of population, what is the range of patients that are going to come. But if that particular, if you just calculate it and you find that there is a greater degree of variability in the number of patients that come from day to day, and the variability is more, your ability to, your range of your prediction is going to be much wider, because your variability is higher. So your lower end, there will be a higher degree of difference between your lower end of the figure and higher end of the figure, simply because your variability is much higher. Your standard deviation or your standard error. Standard deviation is basically a measure of your distribution. It is a measure of the variability. And how is standard deviation computed? It is, if you look at the, if you calculate standard deviation also, it is deviation from the mean. So the more the deviation from the average, the more is the variability. And the more the variability is, the more likely the difference between the lower end of the interval and higher end of the interval. Okay, that is one. And as I said, second is the reliability quotient, which we'll talk about as a 95-99%. Okay, so let me just share my screen. Okay, so this gives your, okay, now let's just look at this. Okay, now suppose a researcher interested in obtaining an estimate of the average level of one enzyme in a certain human population takes a sample of 10 individuals, determines the level of each, and computes a sample mean of 22. Okay, so he takes a sample of 10 individuals. Okay, he computes the level of the enzyme, and the mean comes as 22. Okay, now he says that this variable of interest is normally distributed with a variance of 45. Now, when I say variance of 45, means the standard deviation is the under root of 45. Okay, so to calculate the standard deviation or the standard error, I have to find out the root of it. So what I have done out here, now look at this issue. Now, because I have taken a 95% confidence interval. So in my previous slide, if you see, right, if I compute this is something like 95.45 or something, okay, which is like 2 standard deviations. Okay, if I calculate total these two figures, this is plus minus 2. Okay, approximately 2 is 95.45 or something. Okay, now here, this is just an estimate, does not take an exact figure. The exact figure is for 95% is actually 1.96, but for the time being, we've just taken approximate 95%, and that is plus minus 2 standard deviations. Okay. Now, here my variable of interest is, my standard deviation is 45 divided by 10 under root. Okay. Now, look at this issue, right? Now, my range is being looked at plus minus. Now, what are the factors that I'm using? One is my confidence interval, that is my reliability factor, multiplied by my standard deviation. If my standard deviation was more than that 45, let's say assuming it was 55 or 60, what would have happened? This figure would have been greater than 2.1213, right? And then you find that the interval would increase. If my standard deviation was less than 45, okay, let's assume it was, let's say 30, then this figure of 2.1213 would be less, and therefore my range would be less. Okay, let's try and do this. Let's kind of I'm going to just use an Excel sheet. Can everybody see my screen?
Yes, yes.
Can you see my Excel sheet?
Yes, not Excel sheet, but that PPT.
One sec, let me just do this. Okay, so I had a mean of 22. Okay, and here my standard deviation was 45. My variance was 45, and I had a 10, right? So my standard deviation would be something like
How do we calculate variance?
okay, let me just kind of explain the basic standard deviation. Okay, let's say I have these numbers. Okay, suppose I 3, 4, 45, 23, 56, 34. Okay, I have these figures. Okay, now my average is clear, everybody? This is my average. Okay, right? Now if I had to calculate my deviations from the mean, I would do okay. So in this case, each of the cases I do the deviations. Okay, then I square these deviations. Okay, now when I total these deviations and I divide it by 5, right? This is my variance, and a square root of this is my standard deviation. Everybody okay with this? Right? So the variance is nothing but the square of the standard deviation. Everybody good with this? No sound. Anyway. So let me assume, let me say my standard deviation. Let me just take it as, okay, let me just take it as, okay, let me take my standard deviation as 11, and my number of observations, let me just do this again. I have mean is equal to 22, standard deviation is let's say 10, and standard deviation is it's 15, let's say, and sample sizes okay. So what is my standard error? Everybody good with this? Now, if I want to find out my confidence interval, I'm using a 95% confidence interval, which is plus minus 22. Okay. So what I would do is I will multiply this standard error. Okay. Standard deviation. I will multiply this by okay, and therefore my upper limit is going to be 22 plus, and my lower limit is going to be, right? So this is my upper limit and this is my lower limit. Okay. Now if I
Ma'am, with what did you multiply to get the standard error, ma'am?
so standard error is, if I look at this formula, can you see the formula? I have divided the standard deviation divided by the under root of the sample size.
Sample size, yes, ma'am.
Okay.
And the next something 6.7, how did we get that?
So here, because I have taken 95% interval, okay, I have taken a 95% confidence interval, which is 2 standard deviations. So I multiplied this by 2. This
Two standard errors. Okay, ma'am.
standard error multiplied by 2.
Okay.
Okay. So this becomes 22 plus 6. This becomes my upper limit now. Now what happens is, let's say I increase my standard deviation. Let me make it as 25. Okay. Now see what happens to my confidence interval. Does it increase? One second. Let me just right now my difference is equal to, right now my difference is equal to this. Okay. Now let me say I make my standard deviation as 25. Okay. One sec. Sorry. Let me just control C. Let me just. Okay. Now let me make this as 25. Okay. Now what is my difference? Can you see there is an increase in difference? Simply because what did I do? I increase the standard deviation. Right. So
What happens when we increase the sample size? The standard error.
I haven't increased the sample size. I have right now only increased the standard deviation. Sample size I have left as 20.
Yes, understood.
Okay. I only increase the sample size. Okay. Earlier my standard deviation was 15. Okay. And my sample size was 20. Okay. So then I got this particular figure. Okay. And I got this upper limit event. But the moment I increase the standard deviation, you can see the difference between my upper and lower limit has widened. If I increase my sample size, by the way, okay, okay, if I increase my sample size and I make this 40, what is going to happen? My limit between upper and lower limit is going to decline, right? Because my formula says in terms of my standard deviation, right, my denominator is increasing. So because my denominator is increasing, my sample error is going to come down. Right? Now, the other thing that it varies is basically this 2 figure that I am doing. Okay. Now, if I decline if I make it as 90%, okay, 90%, then it becomes 1.64. Okay. Now, what happens when I do this 1.64? Because when I say 90%, when I put as 90%, okay, then what happens? My limit also compresses. Okay, now it declines. Let me just go back again. This is 2, right? Okay, now let me just control C. Okay. Now let me just change this. Okay, instead of 90%, 95%, let me make it as 90%. And 90% figure is multiplied by 1.64. Now what happens in this case? You will notice that the limit between the upper and the lower will come down. Okay, now this essentially means that now I am less confident. If I want to be more confident, then it means I will have to have a larger range. I want to be more confident, so therefore the range is going to be larger. Okay, because then I am definitely sure 95% confidence that okay, between this range and this range, my population estimate is right. But if I'm only 90% confidence, then my range is kind of smaller. Okay, so it's like all of you have kids, right? Or how many of you have teenage kids? Or older or whatever, right? Or at least teenage kids or somebody low, greater than 15. Okay, right? Now as parents, you say, when when you leave the person unattended, like you'll say that I am 90% confident that this person is going to do this, right? But if you want to be more 95%, then you have a more leeway, you have to give more leeway. I want to be more confident, then that means that degree of leeway has to be given, has to be far greater. That is what you need to understand about constructing confidence intervals. If you have understood this, the rest is all formulas. The rest is it's hardly, it doesn't really, it's not rocket science. Okay, so this is essentially is right. So this Z part is the reliability coefficient, and this is the standard error. Okay, so reliability confidence is Z, which is basically your 1.64 or your 1.96. Okay, and standard error is basically your standard deviation divided by the under root of your sample size. Okay, now when you say 95% confidence, okay, now the entire normal distribution is the size is 1, and when I say 95%, which means 1 minus 0.95 is 0.05, which means at the tails the area under, or the proportion is 0.25 and 0.25. Okay, if I want to look at the area under tails, it has to be 0.25 and 0.25. Okay, that itself will 0.025 and 0.025. Only then you will have 5%. Okay, let me see if I have a formula out here. Okay, unfortunately let me see if I can construct something. Let me see. I'm just wondering whether I can show you something. Insert new slide. My drawing isn't going to be very good, but I'll try. So this is like a normal distribution up here. Okay. It's not very good, but nevertheless. And this is, everybody can see my screen, right? Now this area is 0.50 and this area is also 0.50. Okay. Now when I say 95% confidence interval, which means that it is this area and this area, it will be 0.475 here and it will be 0.475 here. And the area under this, it will be 0.025. 0.025. Okay, because this 0.025 and 0.025 combined is going to make it as 5.5. Right? Everybody's got this? What is 0.475 and 0.475 total equal to? 0.95. Am I right? And 1 minus 9.95 is what? Is 0.05? 1 minus 0.95 is what? 0.05, right? And if I divide it by 2, what will I get?
0.025.
This is exactly what is there. So in my 95% confidence interval, right, I have divided this into this. Okay. So when you say 2 standard deviations, roughly, or it's actually 1.96, okay, that is I am 95% confident that my range is going to be between this, right? And there will be only 0.025, that is, that much, let's say, leeway I can make is about making a mistake about my confidence interval, right? So I am only allowing a 5% error in my estimation. When I do a 90%, confidence interval, then what happens is that this area becomes 90% becomes, right? Let me just, and take another slide. Let me just delete the slide. Right? Then this becomes okay. Now in this case, if I say 90% degree confidence interval, okay, this is my normal distribution. This becomes 0.5. Okay, this obviously is 0.50. This total area is 0.50 and this area is also 0.50. Okay, now when I say 90 degrees confidence interval, so let's say I draw this figure of, right, so this will become 0.45 and this becomes 0.45. Please, wait 1 second, let me just drag this rub. I'm wondering, there is a rubber out here, right? Okay, so this is here. Let me say this is 0.55. Okay, so this figure is, this is 0.5 and this is 0.45. Now what is 0.90? Okay, so if I do 1 minus 0.90, what do I have left? What do I have left? 0.10.
10, yes.
And 0.10 divided by 2 is what?
0.0.
So what I will have in my tails is 0.05 here and 0.05 0.05 here. Got this, everybody? If you've understood the logic of this, then everything is very clear. Okay, let's take another example now. Okay. Okay. A physical therapist wishes to estimate with 99%. Okay, now 99% confidence the mean maximal strength of a particular muscle in a certain group of individuals. He is willing to assume that strength scores are normally distributed with a variance of 144. Okay, a sample of 15 students, 15 subjects who are participated in the experiment yielded a mean of 84.3. Okay, now variance 44, that means my standard deviation is square root of 144, that is 12. My standard error will be 12 under root of 15. Okay, so that gives me a figure of 3.0984. You guys want to calculate, please go ahead and calculate. Okay, now when I say 99.99, okay, now the Z score value of my 0.99 is 2.58, is 2.58. The Z correspondingly Z value of 99% standard value is 2.58. I told you na that the entire normal distribution is 3 standard deviations on the right and 3 standard deviations on the left. Now when I say 99%, which means that I am almost covering the entire area, which means that it is obviously going to be approximately close to 3 standard deviations. So that is why the figure is 2.58. Okay, almost 3. Okay, and therefore to get my confidence interval, I have simply multiplied my Z score, that is 2.58, which is my reliability, coefficient, or you can say confidence coefficient, multiplied by the standard error. Okay, so my confidence interval is ranging from a figure of 76.3 to 92.3. Okay, everybody should be clear with this, right? You can actually do this. Okay, let me just give you the calculator score out here. I have actually done a I'm just going to put it in the chat box. Please go ahead and try it. Okay. Okay, let me just again. Okay. Can you see this? Can you see my screen as calculator net?
No.
You can see it?
Nothing is visible.
Yeah. Can you see this?
Yes.
Okay. So here what is this? This is called a confidence interval estimator. Okay. So let's say, let me just, sample size is, let's say 20. Okay. Average is 84.3. Okay. And my standard deviation was 12, as we talked about. Confidence level is 99, and I calculated it. Okay. So I am getting, you can see the calculations, right? It is 84.3 plus minus 69.2. Okay. If I increase the confidence interval as sample size to 40, right, you can see that the plus minus goes down. if I reduce this confidence interval to 95, you can see again it goes down. Right? So you can experiment, all of you. Please try out. I'm giving you a minute's time. Please use this and experiment and see what happens. I'd request all of you to please experiment. I hope everybody is trying it. I hope everybody's tried it.
Yes.
Right? Everybody's managed to do it.
Yes.
I hope everybody is sounding more confident or feeling more confident. What is the level of confidence? Can we have reactions now?
Ma'am, so if the sample size is increasing, then the error is reducing.
Yes, the range is reduced.
Yes. But
Okay, because you are more certain of things.
Is there any problem if we increase the sample size much more, like?
So sometimes there are limitations, okay, but beyond the point, even if you increase the sample size, okay, sometimes, you know, when there is already very high sample size, a further increase doesn't really make much of a difference. You know, as the central limit theorem goes, as you approach the population size, it's not going to, you know, add any value. So there is a, you know, it improves, but at a declining rate. Let's put it this way. Right? And there is always time and cost of increasing the sample.
Ma'am, is there any problem, like when we repeatedly take samples, like is there any error that happens? I actually listened or read this somewhere that if we repeatedly take samples from the same population, then so there is some error that happens,
No, there is no error if you repeatedly take samples. So this is without replacement. Okay. But again, it depends. I mean, your estimate is likely to be much better if you take repeated samples. But then again, you know, see, again, it depends. See, for example, if I take a sample from the same cluster, it is not necessarily going to improve my estimate. Okay. You know, so for example, one thing that we do when we do regression analysis, we do clustered errors. So if there is, and we use a variable, maybe, you know, maybe a village or whatever it is. So if you find that you are taking, you know, if you have people who are, you know, living in the same cluster, they are more likely to behave in the same manner. Okay, so if I am going to take a sample only from Kerala and I say that this is going to resemble the, you know, Indian population, it's not going to happen, right? If I repeatedly take the sample from Kerala, it doesn't add any value, right?
Yes.
So therefore you have to, you know, look at that. But everybody is okay till now, right? I'm assuming nobody is run away, so I'm assuming everybody is okay. Okay. So this is where the sample size is, okay. Now, you know, then the next thing is what you call is a T distribution, okay. And in a T distribution is when you have sample size which are smaller, okay. So for a Z distribution, you need a sample size of at least 30, okay, and you need to have the population variance, okay. But sometimes, you may have a sample size which is smaller and you do not know the population variance. Okay. In that case, then you take a student t distribution. Okay. So in this case, your t is like x bar minus mu and s divided by standard, and you have degrees of freedom. Okay. So in this case, the logic of how you do it is the same. It's absolutely the same, except earlier you were taking a z distribution, so the value of the z distribution is separate, and in this case you will take a t, the reliability coefficient is measured by a t distribution. It is called a student t distribution. So the values, like earlier you were taking for 95%, you were taking like 1.96 in a z distribution. In a t distribution, it is that value of 9.6 will be slightly greater than 1.96. Okay, so in a t distribution, the values will differ. The rest, the way you do it is entirely is entirely the same. There is the logic is the same. Of course, in a t distribution, you have something called a degrees of freedom. Okay, so if you have your degrees of freedom is basically n minus 1. That means whatever is your size of sample, okay, minus 1, and therefore you use a t distribution table wherein you look at the value of the alpha, and then accordingly you look at the confidence interval. That is okay. Okay, so here in this case, okay, we are looking at the effectiveness of early weight bearing and ankle mobilization estimate. So they found that in 19 subjects, now look at the sample size, it is 19. Okay, the mean isometric was 250.8 with a standard deviation of 30.9. We assume that these 19 subjects, which is considered a random sample from a population of simple. Now, because the sample size was 19, we can't take a t distribution. Okay, so we can't take a z distribution. Okay, so we've taken a t distribution, and you can see that in a 95% confidence interval, this figure is coming as 22.109, but otherwise the way you do it is exactly the same. Okay, there is no change except the distribution differs. Okay, if you are doing something called a difference between means, okay, if you are taking a t test, okay, then in this case you do something like a pooled standard deviation, which is a pooled standard deviation. This is the formula. Okay, and here is n1 is the first sample, the second one is n2 minus 2. Okay, then basically you do the standard error. You've first computed the pooled standard error, and then you've weighted it by the respective samples. Okay, and then you have basically looked at the difference between the two population means. Okay, does anybody want me to do this? I mean, you can. The logic is the same. I mean, it's just in this case we are looking at the difference between two means. Okay, so if I just look at this particular example, the purpose of a study by Ganhur was to determine the effectiveness of an integrated outpatient dual diagnosis treatment for mentally ill subjects. The authors were addressing the problem of substance abuse among people with severe mental disorders. A retrospective chart review was carried on 50 patient reference to the substance abuse mental illness programs at the San Diego Hospital. One of the outcome variables examined was the number of inpatient treatment days of a psychiatric disorder during the year following the end of the program. Among now there were two pairs. One was 18 subjects with schizophrenia. It was 4.7 with a standard deviation of 9.3. For those which was bipolar disorder, it was 8.8 with a standard deviation of 11.5. Right, now we want to know that what is the confidence interval for the difference between the. So you had a confidence interval of a mean. You can also construct a confidence interval of the difference between two means. Okay, so you want to look at one population and the second population, and you say that, what is the maximum, what is the minimum and maximum range of the difference between these two populations. That is what is being done by this example. So you can use confidence intervals also for calculating the difference between two populations. Okay, so in this case, okay, first we did was, I've just repeated the question. First we calculated the pool mean. So there was 18 was the first, 9.3 was the standard deviation, and the second was 11.5. Okay, so the pooled variance was calculated. Okay, and the difference between the two populations was 4.7 minus 8.8. Okay, so they calculated the difference for the 95% with, because there were two subjects, so that is 18 plus 10, 28 minus 2, that is 26 degrees of freedom. Okay, 26, where you can see 18 plus 10 is 28 minus 2, 26 degrees of freedom, and a desired confidence level of 95%. The reliability factor is 2.0055. We use the pooled estimate to calculate the standard error, and so therefore the difference between the two populations can range from minus 12.3 to 4.10. Okay, so because there is a zero, the difference between there, because there is a zero between them, between the lower range and the upper range, you can say that the difference between the two is not substantial. Okay, because there is there is a confidence, we'll come back to this logic later, but basically when you say that, when you talk about difference, if there is a zero between, if the figure 0 comes between the negative, the lower value and the positive value, you can pretty much say that the difference between the two is not significant. Okay, that is what is
What
also
does
there.
minus mean?
What does minus mean? You are looking at the lower range and the upper range, right? Because you've done plus and minus, right? So 4.7 minus 8.8 is what?
Minus
4.1, right? So you are doing minus 4.1 plus 8.20 minus 4.01 minus 8.20. So minus 4.1 plus 8.20 is 4.10.
Yes.
And minus 4.1 minus 8.20 is 12.3. So the range is minus 12.3 to 4.10. Your confidence interval, yeah.
One population to the other, like how we will.
So you are saying essentially what you have computed is that you are 95% sure that the difference between the inpatient treatment days between patients of those which were schizophrenia and bipolar disorder would range from, right, the difference would range from minus 12.3 to plus 4.10. Okay, the difference, that average number of difference. We are not talking about mean. We are talking about the difference, right? So in one case, it could be bipolar disorder, and it could be the difference, if you are looking at, bipolar disorder, right? So in this case, you are looking at bipolar disorder and you are looking at psychiatric disorder, right? So in schizophrenia was 4.7 and bipolar disorder was 8.8. So 8.8 and 4.7, right?
Yes.
Which one was more? 8.8.
Yes.
Okay. So the maximum difference, right? It can be like 8.8 minus, right? And it could also be that schizophrenia could be more than bipolar disorder. In that case, the difference will be, it will be because you're looking at it from, which range are you looking at? It is either schizophrenia minus bipolar or bipolar minus schizophrenia, depending on which range you are looking at. Got it? It's because you're looking at difference. right? One is going to be more, greater and one is going to be lesser. I think I understood what you were saying. Okay, so this is basically a map. Okay, where you are going to use t values or you are going to use z values. Okay. Okay, and this is what I was saying. Okay, when the constructed interval does not include zero, we say that the interval provides evidence that the two population means are not equal. When the interval includes zero, we say that the population means may be equal. This is one way of saying that if you're looking at a difference, if that interval contains zero, then we say that the population means between one population and the other population may roughly be equal. Okay. Okay. So this is basically for your t distribution. Okay, we have just computed the formulas. Okay, and this is basically when you have population variances are when variances are not equal, then there is a slight adjustment that you do. Okay, when you say the population variances, okay, you are assuming. Okay, so this becomes a little technical, so we'll just leave it out. But it's my job to kind of just explain it to you. This is confidence intervals with proportions. Okay, so you have an example where you are computing the confidence interval of something which you measure in terms of a proportion. The logic again is the same. Okay, in this case, your standard error is given by p into q, okay, divided by n and under root. Okay, the z value will remain the z value. It is as you would do reliability factor multiplied by the standard error. In this case, because it is a proportion, the standard error is measured by p into 1 minus p divided by n under root. That's the only difference. If you are looking at difference between two populations and it is measured as a proportion, then this is the formula that you use. Logic again is the same, makes no difference. Okay, so you have the standard error. In this case, you have a pooled standard error that you are doing. Okay, multiplied by the z value, and you will find your confidence intervals with proportions. Okay. Okay, I'm going to stop here. I will take questions right now. Next time we'll finish hypothesis testing, sample size determination and hypothesis testing. Any questions? See, earlier we did something like a binomial distribution, which is a discrete distribution. Then we did a Poisson distribution, which is again discrete. Okay, the third thing that we were using is a continuous distribution, which we talked about is a normal distribution. When we say that, if we have a distribution where the sample size is large enough, right, and it resembles like a normal distribution, then how do you compute your confidence intervals? Okay, so in a Poisson analyzing, then you were not really doing, you were only trying to calculate the probabilities. Okay, in this case also you are calculating probabilities, but you are also calculating confidence intervals, which means that on the basis of a sample you are trying to estimate whether your sample resembles the population within a certain range by using a confidence estimate, which can be as low as 90% or as high as 99%. Okay, now let's hear from any of you how you are going to use what we have done today. Yeah. How does anybody plan to use it? I understand you are going to have your research presentations very soon. Dr. Sunil,
Yeah,
it is slated, right?
yeah.
Okay. Anybody has got any research ideas? What are they planning to do? Nobody has any research ideas about what they want to do. एक्सपेरिमेंट करना है, लीनियर रिग्रेशन करना है, अनोवा करना है, क्या करना है? Nobody wants to do any experiment, huh? Nobody wants to do any research.
Ma'am, I had one doubt in the example
Yeah,
you
yeah,
were.
please.
So, in between that bipolar disorder and schizophrenia, you showed using T test. One sample had minus 13 days. There cannot be minus 13 days, no, ma'am. Like that, I haven't.
That's a, see you. That's exactly what I studied, because you were looking at, when you were looking at the difference. Okay, so one was smaller and one was higher, right? Initially. Now let's say your schizophrenic order was 4.4, and let's say your bipolar was 8.
8. Yes, ma'am.
Okay. Now you were saying 8 minus 4. That's positive. Okay. Now let's say this becomes, your schizophrenic becomes 12. Okay. So then what are you going to do? It will be 8 minus 12. Then it becomes negative, right? That's
so
what
the
we,
distance. Okay.
yeah, difference. We're talking about the difference. The difference can be negative. And you are taking, when you have taken one thing consistently, okay, so if you have taken bipolar as the first and from which you are subtracting schizophrenia, then let's say schizophrenia, so that will come as negative, right?
Okay. So it's like sometimes it is lesser
Yeah,
admissions and sometimes it's more number of
yeah,
days.
absolutely. Right. So it depends from where your starting point is. Not because you always want to get a positive value, it depends from where you are starting. So it has to be in the context of where you have started.
In that formula, which one we put first and which one we put next.
Yeah, yeah. And that is something that only you have to, take care of when you are doing the calculations. Okay, let's have some, I think, in terms of your research ideas. Chat box. I'm looking at the chat box. Anybody has research ideas? Dr. Biju has left. His net was not working out. Dr. Matthews, your research idea. Dr. Khushbu. Everybody needs to make a presentation, I think, Sunil.
Yeah, they can. It's one page ideas, either on quality improvement project or.
Okay. So anyway, we'll do hypothesis testing next time, and which is just an extension, and then we'll go on to ANOVA and linear regression, which makes life a little bit more interesting. Okay, and then we'll see how it goes. Any other questions? Okay, I think nobody is today. Everybody is very silent.
Actually, ma'am, I had like Sri Priya, they said we have some fellows at our clinical posting right now, and everyone
Okay.
was researching what was supposed to go on with the result, because everyone was prepared that some work was soon to come.
Okay.
But we had kept it a suspense as to what kind of work will come. So they were researching on that. whether it
Okay.
would be assignment, whether it would be a presentation. So they are still researching on that.
I think it's still going to be a presentation, right? Okay. Anyway, okay. So let's end and then we'll meet next week and then we'll do confidence intervals and stuff. Okay.
Okay. Thank you, Bindu.
Okay. Thank you, everyone.
Thank you everyone for joining in. We'll see in the next session next Saturday, same time. Till that time, this is Sri Priya along with Dr. Vindya and Dr. Sunil Kumar signing off from the Parliament Desk. Till then, everyone, take care. Bye bye.